Welcome back to QHSE Talks.
Yeah.
A primary explosion in a factory is, it's rarely what actually kills you.
Right, yeah. It's usually just the beginning.
Exactly. I mean, the initial blast might rupture a blender or maybe blow out a vent or even injure an operator who's standing like 3 feet away.
Yeah.
But it's mostly a localized event.
It's contained, mostly.
Yeah, mostly. But it's the shock wave that you really have to worry about.
Yeah.
Because that concussive force travels outward at hundreds of miles per hour. It just slams into the rafters, the I-beams, the top of the ductwork.
And that's where the real hazard is hiding.
Right. And as it hits those surfaces, it knocks, a decade's worth of invisible settled dust right into the air, instantly creating this massive facility-wide cloud.
Just a massive fuel source.
Yeah. And then a fraction of a second later, the fireball from that first blast vents into the room and just ignites that new cloud. That is the secondary explosion.
And that is the one that levels a multi-story building.
Exactly. And takes absolutely everyone inside with it.
Yeah, the physics of that chain reaction are just terrifyingly absolute. I mean, once that secondary cloud is suspended and you introduce the ignition source, there is no manual intervention that can stop the deflagration. It's over.
It's totally over. So today we are dissecting ASP Domain 4, Topic 10. For you associate safety professional candidates prepping for the exam and, the seasoned practitioners out there trying to engineer risk out of their facilities, this is all about applying effective housekeeping practices.
Specifically, we're talking about dust control and the disposal of combustibles.
Right. But we are stripping away that mundane idea of housekeeping as just like a Sunday chore with a broom.
Oh, yeah. It's not just about keeping things pretty.
No, not at all. We are looking at the literal physical fuel for catastrophic industrial events.
And to really understand the gravity of this, I think we need to start by looking at the perspective of the Center for Chemical Process Safety, the CCPS.
Right, the CCPS. What do they say about it?
Well, in their 20 elements of risk-based process safety, particularly when you look at the sections on asset integrity and reliability and conduct of operations, they are completely uncompromising.
Okay, how so?
They explicitly state that dirt, and by dirt they mean grit, grime, dust, spillage, stains, trash, rust, all of it. Dirt is the absolute enemy of reliable operations.
Wow, the absolute enemy. Okay, let's unpack this a bit, because calling a bit of grease on a pump the absolute enemy of operations, well, that might sound like hyperbole to a plant manager.
Oh, sure. Especially one who is like way behind on a production quota.
Exactly.
Yeah.
But the hazard goes so much deeper than aesthetics
Yeah.
or even just worker comfort.
Yeah.
It really comes down to what that dirt hides.
Yes. It actively masks incipient problems, and that is the core operational threat.
Right.
I mean, think about a complex piece of machinery, like, say, a high-pressure hydraulic press. If it's completely caked in a thick layer of oily grime and settled dust, the early warning signs of failure just vanish.
You can't see anything.
Right. You cannot spot a microfracture spiderwebbing across a critical load-bearing component. You can't see a slow, weeping hydraulic fluid leak on a fitting.
Because it's all just covered in sludge.
Exactly. The visual cues that a machine is degrading toward a catastrophic failure state are just completely camouflaged by the lack of housekeeping.
So you are basically operating blind. It's like trying to find a leaky pipe in a flooded basement.
That's a great analogy, yeah.
I mean, if the floor is already covered in an inch of standing sludge, a new puddle from a critical rupture just doesn't register at all. You totally lose your diagnostic capability.
You lose your baseline. And beyond the mechanical masking, there is a really profound psychological component here, too.
Oh, absolutely.
The CCPS guidelines actually note that a lack of housekeeping is a glaring symptom of unorganized, unplanned, and sloppy work. It's basically the industrial application of the broken windows theory.
Right, where one broken window leads to more vandalism because it shows nobody cares.
Exactly. If we connect this to the bigger picture, the physical environment of a facility is the most accurate reflection of its true safety culture.
Yeah, that makes total sense.
I mean, you cannot stand in front of your workforce at a morning toolbox talk and demand high reliability and strict adherence to complex lockout-tagout procedures and then send them out onto a floor that looks like a scrapyard.
Right, because the workforce internalizes the standard of their environment.
Exactly. If management allows trip hazards to sit in the aisles for a week, the operator correctly assumes that bypassing a safety interlock will also be ignored.
The physical environment just constantly undermines the cultural messaging.
Yes, it completely erodes trust.
But, the source material makes a really crucial point here about the division of responsibility. Because workers absolutely must own their specific work areas.
Right. They have to. It's their workspace.
But management must engineer the conditions for success. I mean, you cannot run a production line at like 110% capacity, schedule zero downtime, and then berate the operators for having a dirty floor.
No, you can't. Management has to provide the tools, the dedicated shift time, and the organizational systems to actually maintain that state of cleanliness.
Right. You have to give them a chance to clean.
Exactly. A failure of housekeeping is almost always a failure of resource allocation at the management level. It's not just a failure of operator willpower.
Yeah, and when you look at the strict legal requirements, this concept of systemic resource allocation becomes very apparent.
Let's shift into that legal baseline.
Okay, yeah, because if a messy floor represents a breakdown in management discipline, OSHA provides the rigid framework we have to operate within to prevent that breakdown, right?
They absolutely do.
So looking at the construction standard, OSHA 1926.25 and 1926.258, the foundational rule sounds pretty elementary. It's basically just keep everything in its proper place.
It sounds simple.
Right. Form and scrap lumber with protruding nails and all other debris, well, they must be cleared from work areas, passageways, and stairs.
But the critical language in the OSHA text isn't just about what to remove. It's about the required rhythm of removal.
Ah, the rhythm. Okay.
Yeah, the standard says combustible scrap and debris must be removed at regular intervals.
Regular intervals, so not just whenever we get around to it.
Right. It explicitly rejects the concept of the once-a-month deep clean.
Oh, wow.
Housekeeping is mandated as a continuous, integrated operational task. It is part of the manufacturing or construction process itself, not just an afterthought.
But let's introduce some operational friction here. Because in a high-paced commercial construction project, with razor-thin legends, stopping a crew of highly paid tradespeople to continuously haul scrap lumber and sweep concrete, well, that costs money.
Oh, it definitely delays the schedule.
Right. A superintendent is going to argue that sweeping the floor doesn't pour the foundation or stand up the steel.
They argue that all the time.
So how do we, as safety professionals, balance that very real production pressure with this mandated rhythm of housekeeping?
Well, the argument that continuous housekeeping is a net cost is actually mathematically flawed when you analyze the real data outlined in our study text.
Really? How so?
The return on investment for aggressive housekeeping is immense when you factor in the true cost of clutter. I mean, first, there is just the raw efficiency game.
Like finding your tools.
Exactly. Workers aren't spending 20 minutes searching for a specific tool that's buried under a pile of offcuts, and materials aren't being damaged by being run over or tripped on.
Right. That makes sense. And then there is the macro hazard mitigation.
Huge mitigation.
I mean, think about your own worksite for a second. If the emergency alarm goes off right now,
Right.
Are you running down a clear, unimpeded aisle, or are you hurtling a pallet of materials that was left there temporarily last Tuesday?
That is the ultimate life safety imperative right there.
Yeah.
But even on just a day-to-day basis, slips, trips, and falls remain dominant factors in workers' compensation claims.
Oh, for sure.
I mean, a blocked pathway forces a forklift operator to swerve into a blind spot, and that causes a collision. Or poor staging leads to incompatible chemicals being stored next to each other because the proper designated area is full of trash.
Right, it's a domino effect.
Exactly. The cost of a single major incident, the lost time, the investigation, the medical costs, the regulatory fines, the insurance premium spikes, it all vastly outweighs the hourly cost of maintaining clear aisles.
Yeah, that ROI is pretty undeniable when you frame it like that. So, okay, the macro hazards are visible, the scrap wood, the coiled extension cords, the leaking drums. But the true existential threat in Topic 10 isn't what you trip over.
No, it's not.
It's what you breathe in and what settles invisibly above your head. So let's get into the anatomy of combustible dust.
This is where it gets really dangerous. According to the Globally Harmonized System, GHS Revision 11M, and OSHA's National Emphasis Program on Combustible Dust, the definition is very specific.
Okay, what is it?
It's finely divided solid particles of a substance or mixture that are liable to catch fire or explode on ignition when dispersed in air or other oxidizing media.
Finely divided. Okay, here's where it gets really interesting for the exam. Because the way we measure the explosive potential of these particles is a critical concept for ASP candidates. We need to talk about the QHSE value.
Yes, the dust deflagration index.
Right.
QHSE is the metric that dictates exactly how violently a specific dust will explode.
How violent it is.
Yeah. When engineers design a facility, they need to know exactly what they're dealing with so they can size the explosion venting panels or design the chemical suppression systems.
So how do they figure that out?
To find the QHSE value, Laboratories use a standardized piece of equipment called a 20-liter spherical test apparatus.
A 20-liter sphere. Let's break down how that test actually works, because I think it perfectly illustrates the hazard we're talking about.
It really does.
So they take a specific amount of the dust in question, right? And they inject it into this steel sphere under high pressure to create a perfectly dispersed cloud.
A completely uniform cloud inside the sphere.
And then they trigger a massive ignition source, which is usually a 10 kilojoule chemical igniter.
Yes.
And then the sensors inside the sphere measure the maximum explosion pressure and, crucially, the maximum rate of pressure rise.
That rate of rise is the key. The faster the pressure rises, the more violent the explosion.
Right.
So that rate of pressure rise is normalized for the volume of the test sphere to calculate the cased value. And the exam critical fact that every candidate absolutely must memorize is this: any dust with a cased value greater than 0 is considered explosible.
Greater than 0. And it is volume independent, right?
Yes. Totally volume independent.
Meaning the case value tells you about the inherent chemical and physical violence of the material itself. Like a pile of aluminum dust has the exact same cased value whether you have 1 pound of it or 10,000 pounds.
Exactly. It's the material's fingerprint for destruction.
That's a great way to put it.
Wood dust, agricultural grain dust, coal dust, sugar, plastics, and various metals like aluminum and magnesium, they all have distinct cased values.
But they all explode.
Yes. Aluminum dust, for instance, has an exceptionally high quest, meaning an explosion propagates with terrifying speed and pressure compared to something like, say, coarse wood dust.
But a pile of aluminum dust just sitting on a workbench doesn't spontaneously detonate.
No, it doesn't.
For an explosion to occur, the physics dictate that we need more than just the standard fire triangle of fuel, oxygen, and heat. We need the dust explosion pentagon.
Yes, the pentagon. This is fundamental.
Right.
The pentagon represents the 5 elements that must be present simultaneously. If you remove any single element, you break the chain and prevent the explosion.
Okay, let's go through them.
Element 1 is the fuel, which is obviously the combustible dust itself. Element 2 is oxygen, which is readily available in ambient air.
Right. Can't really get rid of that in a factory.
Exactly. Element 3 is the ignition source. Now, this could be a spark from an angle grinder, an overheated bearing on a conveyor belt, open flames from hot work, or even just an invisible electrostatic discharge.
Okay, so up to that point, we just have a smoldering fire.
Right, just a normal fire triangle.
I mean, if you put a match to a solid pile of wood dust, it chars, it smokes, it might catch fire, but it certainly doesn't level the building.
No, it just burns on the surface.
Right, so to turn that fire into a bomb, we need the final 2 elements.
Yes. Element 4 is dispersion. The fine particles must be lofted and suspended in the air to form a cloud.
Let's visualize the mechanism of dispersion for a second, because it's really all about surface area.
It's entirely about surface area.
Think about trying to light a solid oak log with a single match. It's practically impossible. The mass is too dense, and there just isn't enough surface area exposed to the oxygen to sustain combustion.
Right, the heat just dissipates.
But if you take that same log and run it through a wood chipper, and then run those chips through a grinder until you have this ultra-fine flour-like dust, well, you haven't changed the chemical composition of the wood at all.
Not one bit.
You've just exponentially increased its surface area. So when you throw that dust into the air, suddenly every single microscopic particle is entirely surrounded by oxygen.
And that is when things get deadly. When that dispersed cloud is ignited, the combustion wave travels from particle to particle almost instantaneously.
Because they're so close together.
Exactly. Because the surface area is so vast, the fuel oxidizes at a staggering rate, releasing massive amounts of heat and gas.
Wow.
But, even a dispersed cloud burning in an open field just creates a rapid flash fire. I mean, it's dangerous, you'll get severely burned, but it doesn't generate the destructive pressure wave that knocks down walls.
Right. For that, we need the final element.
Element 5. Confinement.
Confinement.
When that rapid oxidation and gas expansion occurs inside a closed space, whether that is inside the casing of a dust collector or inside a storage silo, or even just within the walls of a manufacturing facility, the gases have nowhere to go.
The pressure just builds.
It spikes exponentially in milliseconds, and it quickly exceeds the structural yield strength of the enclosure.
And then it pops.
Violently. The enclosure ruptures, and that is the explosion.
So fuel, oxygen, ignition, dispersion, and confinement. The pentagon.
That's the formula.
And these 5 elements are constantly threatening to align in standard, everyday manufacturing environments. I mean, we aren't just talking about specialized munition plants here.
Oh, no. Not at all.
We're talking grain silos, lumber mills, food processing plants handling cornstarch or flour, metalworking shops. I mean, if you are milling, grinding, crushing, or conveying solid materials, you are generating this fuel.
You are creating the hazard every single day. Which brings us back to the nightmare scenario you described at the very beginning of our analysis.
The secondary explosion.
Yes. The GHS guidelines highlight this as the absolute most devastating consequence of poor housekeeping.
Because the primary explosion is often relatively small, right?
Usually, yes. It might occur inside a piece of enclosed machinery where all 5 elements of the Pentagon just naturally align during normal operations.
Like a blender or a bucket elevator. You know, the 2008 Imperial Sugar Refinery explosion in Port Wentworth, Georgia, is like the ultimate tragic textbook case study of this exact mechanism.
It really is. The U.S. Chemical Safety Board investigation detailed exactly how a localized failure turned into a massive catastrophe, strictly because of accumulated dust.
It's so sad.
It is. In that incident, the primary explosion occurred inside a steel conveyor enclosure that was transporting granulated sugar.
Okay, so the enclosure provided the confinement.
Right. And the moving sugar provided the dust and the dispersion, and then an overheated bearing or some similar mechanical failure likely provided the ignition.
So the primary blast ruptured the conveyor panel.
Yes. And here is where the physics of the secondary blast completely take over.
Right.
The concussive shock wave from that primary explosion breached the conveyor and traveled through the massive packaging facility at the speed of sound.
The speed of sound.
Mm-hmm.
And because housekeeping was severely deficient, years of fine sugar dust had accumulated on every horizontal surface in that facility.
Everywhere.
It was inches thick on the overhead light fixtures, resting on the structural steel girders, stacked on top of the ventilation ducts. Basically out of sight, out of mind.
Exactly. And that shock wave acted as a mechanical force. It violently shook the entire building structure.
Every beam and duct vibrating simultaneously.
Yes. Dislodging thousands of pounds of settled sugar dust all at once.
Oh my God.
As that dust fell, it perfectly mixed with the ambient air, creating a massive facility-wide dispersion. Element 4 of the Pentagon was instantly achieved on a massive scale.
And the ignition source wasn't just a tiny spark this time. It was the expanding fireball venting out of the ruptured conveyor from the primary blast.
Yes, that fireball hit the newly formed massive dust cloud.
Because the exterior walls and roof of the packaging building provided the confinement.
The resulting secondary explosion generated pressures that completely obliterated the reinforced concrete floors and blew out the brick walls.
14 people died.
14 fatalities, and it was all entirely preventable through housekeeping. It's chilling. This is exactly why Domain 4 connects housekeeping directly to fire and explosion prevention. I mean, when you mandate the cleaning of overhead pipes and the tops of cabinets, you are not engaging in spring cleaning.
No, you are systematically disarming a thermobaric bomb.
Right. You are permanently removing the fuel source so that if a piece of equipment does fail and cause a primary deflagration, there is nothing for the shock wave to shake loose.
Exactly. The chain reaction dies immediately.
So if the stakes are literally that high, how much dust is actually considered lethal? I mean, we can't build a sterile, microchip-level clean room in the middle of a working lumber mill.
That's a practical reality, yes.
Where is the exact regulatory line between a dusty day and a ticking time bomb?
Well, the industrial hygiene sources and NFPA standards, specifically NFPA 654, give us the golden rule that every safety professional must know for the exam and the field.
Okay, what is it?
The settled dust layer thickness should never exceed 18 of an inch.
18 of an inch, wow. That is roughly the thickness of a paperclip, or maybe a quarter. It is incredibly thin. It is very thin.
But how did the engineers arrive at that specific measurement? Why not a quarter of an inch or a full inch? Why 18?
It comes down to the math behind the minimum explosible concentration, or MEC.
MEC.
The MEC is the lowest concentration of combustible dust suspended in the air that can actually propagate a deflagration.
So if the cloud is too thin, it won't pop.
Right. If the particles are too far apart for the combustion wave to jump from one to the next, the fire just starves.
Got it. So they calculated how much settled dust it takes to hit that MEC when he gets lofted into the air.
Precisely. The engineers calculated the bulk density of typical combustible dusts. They often assume around 75 pounds per cubic foot for this baseline.
Okay.
And they determined that if you have a uniform dust layer of just 18 of an inch, covering merely 5% of the floor area of a room.
Wait, only 5% of the room.
Just 5%.
Right.
And that dust is suddenly dispersed into a cloud extending up to a standard 10-foot ceiling height. The resulting concentration in the air will reach the minimum explosible concentration.
That is staggering.
It really is.
Just 18 of an inch, covering only 5% of the room's surface area, is enough to create a lethal bomb if it gets shaken into the air.
That illustrates exactly why constant vigilance is required. It does not take long for a busy woodworking router or an agricultural grain leg to generate a paperclip's thickness of dust.
Not long at all. So if your facility has settled dust exceeding 18 of an inch, what does that mean?
It means your current engineering controls are failing. Full stop.
Right.
The hierarchy of controls dictates that you cannot just rely on workers constantly sweeping with a broom. You must attack the hazard at the source.
Which means?
This requires enhanced process enclosures to keep the dust inside the machinery in the first place and robust local exhaust ventilation.
Okay, let's talk about the mechanics of that exhaust ventilation. How does a dust collection system actually prevent the hazard from accumulating?
Well, the GHS Rev 11 text is clear that where combustible dusts cannot be avoided, exhaust ventilation must be used to prevent the concentration from ever reaching the explosible range. And the engineering mechanism here relies on capture velocity.
Capture velocity, okay.
The exhaust hoods pull a specific volume of air at a high enough velocity to overcome the ambient air currents. It physically drags the particulate matter into the ductwork before it ever has a chance to settle on the floor or the rafters.
So it grabs it right as it's made.
Exactly. It operates on negative pressure, ensuring the dust is captured at the exact point of generation, like a saw blade or a grinding wheel, and safely conveyed to a properly vented and suppressed dust collector located safely outside the building.
Okay, but let's play devil's advocate.
Yeah.
Let's say the local exhaust ventilation is underperforming, or maybe it's just a heavily utilized area and I'm doing a site walkthrough.
Okay, paint the picture.
I look up and see a 1/4 inch of dust accumulated on the casing of a large electric motor.
That's a violation right there.
Right, it is over the 18-inch limit. And the motor is running hot
Yeah.
because the dust is basically acting as an insulating blanket.
Yeah.
Now, my instinct to clean it quickly and get back to work is to grab the nearest 90 psi compressed air hose, point it at the motor, and just blow all that dust off. It's fast, it gets the dust out of the fins of the motor, and I've technically cleaned the surface.
Oh boy.
Can I do that?
Absolutely. Unequivocally, no.
Not at all.
The source material and OSHA enforcement guidelines are incredibly strict on this point. Cleaning with compressed air wands must never be permitted when dealing with combustible dust.
Why? Why is an air hose banned so strictly?
Think back to the dust explosion Pentagon and the mechanism of dispersion we discussed earlier.
Okay.
What are you physically doing when you hit a settled pile of dust with 90 psi of compressed air?
Blowing it everywhere.
Yes. You are violently injecting it into the atmosphere. You are artificially creating the exact massive dispersed cloud that the secondary explosion relies on.
Oh, wow.
You are taking a settled, relatively stable fuel and intentionally turning it into an optimal explosive mixture.
So you're literally building the bomb yourself.
Yes.
And you are doing it while standing right in the middle of it.
Exactly. And the ignition source doesn't even have to be a massive fireball.
No.
If you blow that dust off an electric motor, the motor itself might be hot enough to hit the auto-ignition temperature of the dust.
That's terrifying.
Or a nearby worker might be grinding a weld. Or, most insidiously, the compressed air moving rapidly over the plastic nozzle of the air hose can generate static electricity.
Just the air moving.
Just the air friction. It causes a tiny arc that ignites the cloud you just created.
That is wild.
And, even aggressive dry sweeping with a standard push broom is banned in many of these environments because it lofts too much fine particulate into the breathing zone and creates a localized hazardous cloud.
Okay, so what is the operational alternative then? I mean, if we can't blow it away and we can't dry sweep it, how do we legally and safely remove that 1/4 inch of dust?
You must use methods that remove the dust without dispersing it.
Like what?
The primary approved method is vacuuming. But, and this is a critical distinction for the exam and for real-world safety, you cannot use a standard commercial wet-dry shop vacuum that you bought at a local hardware store.
Wait, why not? A vacuum's a vacuum, right?
Let's explain why a standard vacuum is basically an ignition source waiting to happen. It all comes down to the triboelectric effect.
The tribo what?
Triboelectric effect, yes. When dust particles are sucked into a vacuum, they constantly rub against each other and against the inside of the plastic vacuum hose.
Okay, lots of friction.
Right. This friction strips electrons from the particles, generating a massive static electrical charge through triboelectric charging.
Like rubbing a balloon on your hair.
Exactly like that, but on an industrial scale. In a standard vacuum, this charge builds up on the plastic hose and the ungrounded metal components until it finally arcs, creating a high-energy spark.
And where does that spark happen?
Right inside the canister of the vacuum.
Which is currently filled with a perfectly dispersed cloud of combustible dust.
Exactly. Which means the vacuum cleaner itself becomes a confined dust explosion that blows up right in the operator's hands.
Man, everything in this topic is a bomb.
It really is. So to prevent this, you must use specialized, intrinsically safe, explosion-proof industrial vacuums that are specifically rated for combustible dust environments.
So how are those engineered differently? How do they stop the static?
Well, they utilize conductive or static dissipative hoses. Every single component, from the nozzle to the motor casing, is physically bonded and grounded to earth.
So the electricity just flows into the ground.
Exactly. The static charge is safely bled off into the ground before it can ever accumulate enough potential to spark.
That's brilliant.
And furthermore, the motors are completely sealed and isolated from the airstream so that the electrical brushes inside the motor cannot ignite the dust passing through.
Okay, so specialized vacuums. Are there any other approved methods?
The other approved approach mentioned in the text is wet methods.
Wet methods, like washing it down.
Using water-based dust suppression systems, yeah. You can gently wash down the areas, or use misting systems to knock the suspended dust out of the air and keep it damp on the floor.
And the chemistry here is pretty simple, right? Wet dust cannot disperse into a cloud.
Exactly. And the water acts as a massive heat sink, preventing combustion entirely.
Makes sense. Obviously, this only works if your product and equipment can actually tolerate water.
Right, you can't wash down a flour bakery without creating, concrete-like dough everywhere.
Yeah, that would be a nightmare. But chemically, a wet dust layer is rendered inert.
It is. And the facility's written housekeeping plan must explicitly specify these approved methods. And as the GHS notes, regular documented inspections for excessive dust levels, particularly in priority areas like overheads, concealed drop ceilings, and ductwork, are strictly required.
Okay, so we have thoroughly mapped out the microscopic fuel, the combustible dust, the Canis value, the 18-inch limit, the mechanics of dispersion, and the engineering of intrinsically safe vacuums.
We covered a lot there.
But an industrial worksite has a lot more fire hazards than just dust.
Oh, definitely.
Let's scale up to the macroscopic fuel, the physical trash, the waste, the byproducts of daily operations. Let's talk about the disposal of combustibles.
This is a huge part of Topic 10. While dust is the invisible atmospheric threat, we cannot ignore the highly visible everyday hazards.
Right.
The OSHA standards, specifically Subpart H regarding hazardous materials, and the construction housekeeping standards we discussed earlier lay out very rigid protocols for combustible waste materials.
And what does that encompass?
This encompasses oily rags, scrap lumber, flammable liquid containers, solvent-soaked wipes, and just general refuse.
So how should a site practically manage this combustible trash so they don't run afoul of OSHA, or worse, initiate a fire that burns the plant to the ground?
It all comes down to strict containment and segregation.
Segregation, okay.
OSHA requires that specific containers be provided for the collection and separation of waste. You cannot utilize a single massive roll-off dumpster for everything.
You can't just throw it all in one bin.
No, you have to separate the chemical and the physical hazards. And the vital compliance point that shows up continuously in the texts is this: containers used for garbage and other oily, flammable, or hazardous wastes, like caustics, harmful dusts, or solvent rags, must be equipped with covers.
Must have covers. Okay, let's talk about the engineering behind those covers, because they aren't just plastic lids meant to keep the smell in.
No, they are highly engineered, life-saving safety devices.
We are talking about the classic red, self-closing, oily rag can.
Exactly. The source texts specifically describe self-closing containers designed for storing cloths and wipes contaminated with flammable liquids or oils.
And the design specifics are just brilliant in their simplicity.
They really are. They are typically cylindrical metal cans with a raised bottom.
Why a raised bottom?
This elevated base allows airflow underneath the can, which is a critical design feature to prevent conductive heat transfer to the floor if the contents do catch fire.
Well, that makes sense. So it doesn't burn the floor.
Yeah.
But the core safety mechanism is the lid, right?
Yes.
It's usually operated by a foot lever. You step on the pedal, the lid raises, you drop the solvent-soaked rag inside, and the moment you release the lever, the lid slams shut under its own weight or via spring tension.
That automatic self-closing mechanism is so critical.
Right. Because why not just use a lid you place on top manually?
Well, why do you think?
Because human nature basically guarantees someone will forget to put the lid back on.
Every single time.
And with oily rags, leaving the lid off invites thermal runaway. We need to talk about the chemistry of spontaneous combustion because this is the exact mechanism that burns down woodworking shops and automotive garages every single year.
It happens all the time.
I mean, think about a cotton rag soaked in linseed oil or a similar finishing oil. As that oil sits on the rag, it reacts with the oxygen in the air. This oxidation process is exothermic. It releases heat.
Right, it generates its own heat.
Now, if you lay that rag flat on a concrete floor, the heat just dissipates into the air and nothing happens.
It just dries out.
Exactly.
Yeah.
But if you crumple that rag up or throw it into a pile with 50 other oily rags in a standard open trash can, the dynamics totally change.
The cotton fibers of the rags act as incredible insulation.
Yes. The heat generated by the exothermic oxidation of the oil is trapped inside the pile.
It can't escape.
Because the heat can't escape, the temperature inside the pile begins to rise. And as the temperature rises, the rate of oxidation speeds up, which generates even more heat, which speeds up the oxidation even further.
It's a vicious, accelerating cycle of thermal runaway.
Exactly. Eventually, the temperature deep inside that pile of rags reaches the auto-ignition temperature of the cotton or the solvent.
And at that exact moment, the pile bursts into flames entirely on its own.
Entirely on its own. No spark, no match, no hot work required. The chemistry simply takes its inevitable course.
And this is exactly where the self-closing can breaks the chain.
How does it do it?
If that rag is dropped inside a covered self-closing container, the exact same oxidation process begins. The rag generates heat, it starts to smolder.
Right, the chemistry doesn't change.
But because the heavy metal lid slammed shut the moment the worker's foot came off the pedal, the container is virtually airtight.
Ah, so it starves it.
It starves the reaction of oxygen. The fire triangle requires fuel, heat, and oxygen. The container limits the oxygen to whatever small volume of air is trapped inside the can.
Which isn't much.
No. Once the smoldering rag consumes that small amount of oxygen, the chemical reaction just stops. The fire chokes itself out before it can ever transition into open flaming combustion.
That is so elegant.
Furthermore, the limited size of these specific containers intentionally restricts the total fuel load. I mean, you physically cannot pack 1,000 oily rags into one standard safety can.
Right, which inherently limits the potential energy of the hazard.
Exactly.
But, eventually those self-closing cans fill up. And if they overflow, the lid gets propped open by a rag, completely defeating the entire safety mechanism.
Which brings us back to the mandated rhythm of operations we discussed earlier. The regulations explicitly state these covered containers must be emptied at frequent and regular intervals.
So they must be emptied at the end of every single shift.
It is a non-negotiable operational task.
This raises an important question, actually. What happens to the waste once it leaves the safety can? I mean, if a facility is in a remote area and disposes of waste materials through burning like scrap lumber or paper, how is that managed?
The sources address this directly, actually. If a facility disposes of waste materials through burning, employers and workers must comply strictly with local fire regulations.
So it's never a decentralized free-for-all.
Never. You need burn permits, designated safe zones, and fire watches. And crucially, until that hazardous waste is actually removed from the site or safely disposed of by a hazardous waste contractor or legally burned, all solvent waste, oily rags, and flammable liquids must remain kept in those fire-resistant covered containers.
You cannot take them out of the safety can at the end of the shift and just throw them in an open pile out back, waiting for a burn day next week.
Absolutely not. The hazard must remain contained until the exact moment of safe destruction.
We also need to connect housekeeping to special high-risk operations, because housekeeping isn't just a general environmental baseline, right? It is deeply legally tied to specific tasks.
Very deeply tied.
I'm looking at the OSHA 1910.119 Process Safety Management Standard here, specifically around mechanical integrity and the general fire prevention rules governing hot work.
Hot work is the ultimate stress test of your housekeeping program.
It really is.
Hot work includes welding, cutting, brazing, grinding, or any spark-producing operations.
Basically anything that makes fire or sparks.
Right. When you are welding, you are manipulating a torch that is throwing molten slag and sparks at over 3,000 degrees Fahrenheit. If your housekeeping is poor, you are practically guaranteeing a severe fire.
And the sources mandate extreme precautions here. Before a hot work permit can even be authorized by the safety manager, the area must be physically made safe.
And what does that mean practically?
This usually means a mandatory 35-foot radius cleared of all combustible materials.
35 feet in every direction.
Right, and if there are heavy dust concentrations on the floor or the equipment, they must be meticulously cleaned up using the proper intrinsically safe vacuums or wet methods we discussed. You cannot just sweep it out of the way.
Because the welding sparks will find the airborne dust.
Exactly. But the regulations also account for the reality of industrial environments. I mean, what if you cannot move the combustible material?
That happens a lot.
Right. What if you have to weld a bracket right next to a stationary wooden structural beam or next to a piece of processing equipment that just cannot be relocated?
Then you must employ engineered shielding.
Shielding, okay.
If there are immovable fire hazards, positive physical measures must be taken to confine the heat, the sparks, and the molten slag.
You must deploy fire-resistant welding blankets, specialized shielding, or sheet metal to completely isolate those immovable hazards from the spark trajectory.
Yes. And because the heat from a welding arc can transfer through steel bulkheads through conduction.
Oh, I didn't even think of that.
Oh, yeah. And because a single tiny spark can bounce under a cabinet and smolder invisibly in a pile of forgotten dust for hours before bursting into flames, a dedicated fire watch is required.
A dedicated person just watching.
Yes. A worker with a fire extinguisher must be stationed to monitor the area during the entire hot work operation and, critically, for at least 30 minutes after all hot work has concluded.
It all connects perfectly, doesn't it? The invisible dust on the rafters, the chemistry of the oily rags, the 3,000-degree sparks from the welding torch. It all comes back to controlling the fuel through relentless, systematic housekeeping.
It really is the ultimate baseline. If you cannot control the fundamental accumulation of fuel in your facility, no amount of advanced fire suppression technology or complex safety management software will save you when the ignition source finally arrives.
We have covered a massive amount of technical and operational ground today. Let's distill this into the absolute essentials.
Good idea.
For those of you analyzing these sources for your operational practice or preparing for the ASP exam, these are the non-negotiable takeaways you need to have locked in.
First, understand the dust deflagration index. Remember that any COEST value greater than 0 means the dust is explosible, and it is a volume-independent metric of violence.
Second, memorize the dust explosion pentagon: fuel, oxygen, ignition source, dispersion, and confinement. Know exactly how the addition of dispersion and confinement turns a standard fire into a catastrophic deflagration.
Third, the 18-inch rule. Settled dust layers must never exceed 18 of an inch, because that is the threshold that, when lofted, hits the minimum explosible concentration.
Fourth, the absolute ban on compressed air cleaning and dry sweeping for combustible dust. You cannot use air wands to clean. It artificially creates the dispersion leg of the pentagon. You must use intrinsically safe, bonded, and grounded vacuums or wet methods.
And finally, the vital need for covered, self-closing containers for combustible and oily waste. They are engineered to break the thermal runaway cycle of spontaneous combustion, and they must be emptied at regular intervals.
Those are the core technical competencies. Understanding these rules, and more importantly, understanding the physics, the chemistry, and the mechanisms behind why they exist, well, that will elevate your hazard recognition far beyond just a simple checklist.
Absolutely.
But before we sign off, I want to leave you with a final thought to mull over, something that builds on the CCPS guidelines we discussed at the very beginning.
Okay, what is it?
Imagine a senior OSHA auditor or an insurance underwriter walks into your facility tomorrow.
Always a stressful day.
Right. But before they look at a single piece of paperwork, before they review your training logs, your hot work permits, or your complex process safety management binders, they are going to look at your floors.
They absolutely will.
They are going to look in the dark corners, and they're going to shine a flashlight on the overhead pipes. Your housekeeping tells them your entire safety story in the first 60 seconds.
It is a question every safety professional and facility manager must confront. The physical environment is the unfiltered mirror of your operational discipline.
Is it possible that the deceptively mundane act of sweeping a floor, safely disposing of a solvent rag, or vacuuming the rafters is actually the most accurate predictive metric for your company's risk of a catastrophic event?
It very well might be.
Because if a management team cannot effectively coordinate the removal of the dirt they can see, how can they possibly be trusted to manage the complex, highly hazardous chemical processes they can't?
That's a powerful point.
Thank you for joining this session of QHSE Talks. We hope this analysis of ASP Domain 4, Topic 10, arms you with the technical depth required to master your craft. Walk out onto your site tomorrow and look at the environment with a completely new perspective on the physics of fuel.
Until next time, stay safe.
Stay safe, everyone.